I'm Iwasawa from Japan, and the title of my talk is Classic False Coin Puzzles Without Mathematical Induction. But my actual talk in only 6 minutes would be better described as one classic false coin puzzle and hints for some other topics. Anyway, let me start. Our problem is a classic false coin puzzle with a balanced scale and no other weights. Among M coins, there is one and only one counterfeit. The counterfeit is either a bit heavier or lighter than the others. You don't need to determine whether it is heavier or lighter. The question is, what is the maximum number of coins M for which you can make sure to identify the false coin in n weighings, right? And yeah, of course, there are some conditions to be addressed, to be more precise, but they are only common sense conditions, which I believe I can skip for now. And okay, all right, I'm sorry. But yeah, it turns out that if the number of wings n is 3, the maximum number of coins is 13. Sure, of course, this is our theme of this time. And in general, the answer is 3 to the power of n minus 1 all over 2. And a typical solution of this problem, as far as I see in the literature, consists of more than 100 lines of mathematical induction. Even a solution with a more sophisticated approach using information theory consists of not much less than 100 lines, but it still needs to divide the situation into so many cases. But I have found a much shorter solution which can be written on only 3 slides, yeah, which you can see flipping by too quickly, I'm sorry, on the screen. So because time is short, I'll give just an outline of this solution. And from an argument of information theory, we easily find that m is less than or equal to 3 to the power of n plus 1 over 2. And in the most tricky part of this solution, it can be proved in a few sentences that you can make m equal to 3 to the power of n plus 1 over 2 if you have another coin known to be genuine when you start. But we don't have any coins apart from the original group. However, after the first weighing, you will have at least one coin which you can be sure is genuine, so that the difference is only at the beginning. Therefore, the true m is smaller by 1 than the mentioned number, 3 to the power of n plus 1 over 2. That is to say, m is 3 to the power of n minus 1 over 2. That's what we wanted. Done. Okay, but what have I done? I admit that my explanation was too brief, but still, I hope you see that this classic puzzle has a nice solution that a recreational mathematics lover like you may enjoy. And to stimulate your curiosity, I will leave you with a small challenge. Please imagine a situation in which during a procedure to identify a unique counterfeit from 15 coins, you have mistakenly mixed coins so that 13 of them are now ones, each of which can be a counterfeit, heavy or light. Another is a coin which can be heavy but can't be light. And the last coin is the one which can be light but can't be heavy. In this situation, the question is, how can you make sure to identify the counterfeit from the 15 coins in only 3 weighings? As the maximum number of coins from which you can certainly identify the counterfeit is already 13, as we have seen it, this challenge is really something. But if you have grasped the essence of this kind of puzzle, you can solve it quickly and logically. Can you? And by the way, I have several other topics which I really would like to share with you when we have time. So two examples are these. One, a very simple proof of impossibility of 14-15 puzzle, which you know very much, without relying on the theory of permutation group. And another is simple solution for the random intervals problem in Peter Winkler's mathematical puzzles. The latter one is this, which I don't explain now, but it's very interesting. And in fact, I have found very nice solutions for those problems. I recently wrote several articles on those topics for a Japanese mathematics magazine. And finally, my conclusion of this talk is, please come and talk to me if you are interested in some of the topics I mentioned. Thank you.
Fantastic. You've got 30 seconds.
Yeah, thank you very much. And I was asked to make an announcement from ARMJ. It's a little small, I think, but ARMJ is the Academy of Recreational Mathematics Japan, and they publish English issue once a year, and we really would like as many of you as possible to join us. And the chairman, Yoshi Kotani, where is he? Oh, yeah, he is. He has a table at sales room B. So please, so ask him. So what can you do? Thank you.
Fantastic. Thank you.